Okay, so let's go ahead and get started today. So today's lecture is how to do loops in assembly. Now, in your programming class, did you talk about loops? Okay, good. Because I was, you might remember when we first brought up a flow chart, I was kind of surprised that flow charts aren't talked about in a first programming class, but I guess things have changed since I took a programming class out, because that was like day one. But anyway, I would imagine that they still talk about loops, so okay, just wanted to make sure though. All right, so if you've done loops in a different language, you're gonna see it's very similar. And it's just really an extension of what we did last week. Conditional statements in assembly where you're using branch instructions. Okay, you'll see also when you're doing loops in assembly, there's branch instructions. The difference is now you're just doing a set of instructions repeatedly, based on a condition. So, okay. Also, I just want to remind people, and this is on Canvas. It hasn't changed. Okay, I'm just giving you a heads up. The midterm, it's a week from Tuesday of next week. So it's not next week, it's the week after. It's on Valentine's Day, actually, February 4th. And I'll make some comments about it once I'm done with the lecture part. The lecture shouldn't be that long today. Okay. And then, I have an example. It's one of the parts out of software number 3, part 2, and then you're assigned part 1 of software number 3. Okay, so that's the assignment that will be due Monday of next week. Remember the reg file that you started working on last time, that's due tomorrow. Okay. Okay, but I think the easiest way to explain loops and see how it's done in assembly is just by doing some examples. So that's what I have up here, 3 different examples. Well, I guess 4, because this one has 2 different ways of doing the same thing. Okay, but like always, before you write any assembly code for any type of situation, you always want to have a flow chart. So this shows a flow chart of a certain kind of loop. You can see here we have a process where we're setting just a integer I to 0. Then we have a condition, right? We're testing that integer to 10. This is 10 and base 10. It's not 1, 0 binary. And then based on whether this is true or not, we're going to repeat some instructions, then increment this integer that we have made equal 0, and then just go back and do the same decision. Right? And we just loop through this the number of times until our condition is met and we fall out of the loop. Okay, so this is what the assembly code would look like for this flow chart. So the first thing we would need to do, and this is something that you always have to keep in mind, and we actually did this last class with the reg file. Remember with the reg file, once we created the array, right, that was going to represent the registers in the reg file, what did we do next? Yeah, we initialized all the contents of the array to 0. So you can't assume that a register has 0 to begin with. Right? At the start, the contents of the register are unknown. They could all be 0s, but they could also have some 1s. Okay, so you should never take for granted that a register is 0 to begin with. You need to make it 0. Now, of course, with the reg file, if you did your coding correctly, your modeling correctly, you should have it such that register 0 is always 0 now. Okay, but other than that, you can't count on a register being all 0s. Okay, so that's the need for this. Okay, is that we're going to use register 5 to hold our count. Okay, so this is initializing register 5 to 0.
Actually, the good thing about your markers for me because my video is running out, so that was good timing.
Okay, so this is the register that we're gonna use as a counter. That every time we go through the loop, we're gonna increment that by 1. Okay, now, we gotta compare that counter against this value of 10, so we have to put that into a register. Okay, so that's what this load immediate does. It's just putting, our max count info into register 6. You've all used load immediate commands, right? So, okay, so now we're gonna go ahead and do our condition, right? We're gonna compare our I value to this max count that we put into register 6. And if our counter is equal to or greater than our max count, we're done. But if not, now we're going to do the repeated instructions. Okay, so here, whatever you want to do more than 1 time, whatever that may be, that's what you would have here. Okay, then once you're done with those repeated instructions, well, we're going to increment our counter, which again is register 5, we're going to increment it by 1. So we're using this add I command. Remember what this add I command does, it takes this immediate, this number, which is 1, just adds it to the contents of register 5, and then puts the results in register 5. Right, so we started with 0, this would just add 1 to it, and now the result of 1 would be put in register 5. You jump back, and again, here's a jump, which is an unconditional branch, so it will just go to the instruction where the label is, and it just repeats, right? That it's just going to keep doing this until our contents of register 5 equal what's in register 6, right? And at that time, it would come out of a loop, and then whatever you put here, now it's going to execute whatever's below this jump instruction.
When you put n by x, is that actually the correct 10 or is that like 16?
Okay, well, we're putting 10 here, and specifically, I think what your question is regarding is RARs, right? The software we use to test our programs. In RARs, if you just put a number here, it defaults to base 10. If you wanted this to be a base 16, you would have to do the 0x and 10. So if this was 0x10, RARs is going to take it as a hex of 16. Okay, but if you just put 10, it will take it as a base 10. Okay. Any other questions? Okay, well, here's some code that will do the same thing. Okay, so this is like 2 separate programs. Okay, here's one program, here's the other program. Can you see what the difference between this program and this program is? Subtracting, that's true.
What's that is equals, you only initialize it to
Right, we're only initializing it to mask because of why. It has to do with what you were saying. We're subtracting, so how are we counting here? In what direction are we counting? Yeah, upright. Because we initialize, we're essentially initializing a counter to 0. Every time we go through the loop, we're incrementing by 1 until we reach some value, right? Then we stop. Here, we just initialize the max value, we count down, right? Until it's 0, then we drop out of it. Right? So you see here, we're counting down. Or excuse me, here we're counting up. Sorry. Here we're counting up. Here we're counting down. And if you compare the number of instructions we have, assuming the repeated instructions are the same number, it's like 1 less instruction, right? When you're counting down. So I'll get to your question in a second. So, where that would matter, I mean, if you had a case where you absolutely wanted to use the least amount of instructions, right? Because remember, every instruction takes time to be processed, right? So the more instructions you have, the more processing time. So I mean, if you were in a situation where one instruction mattered, you're gonna see that one instruction for the otter isn't a whole lot of time. You know, this would be a more efficient way since it has one less instruction. Now, in this class, although there is one exception to what I'm gonna say, in this class, we really don't look at whether your programs are the most efficient. You know, if you're using more instructions than absolutely necessary, that's fine. Now, there is one exception to that that will have to do with the part one assignment that you'll do, you know, starting today, and I'll mention that when we get there. But you have a question?
Yeah, it's a sort of track. All the time.
Oh, that's a good question. Yeah, there is a subtract command. You know, I haven't really used that command. I have to look at the description to see if there's any differences. But you can definitely use an add I here because, okay, and this again is where looking at your instruction manual is really helpful. If you look at the add I command, it tells us that the immediate, which is a 12-bit immediate, is that it's in 2's complement form and it's going to be sign extended. So once you see that a command is treating, well, a command that has an immediate, once you see that it's sign extending the immediate, that tells you it can be negative because it's 2's complement, right? But if you were to look at a command, I don't know, let's look at the subtract command. SUB. Let's see, subtracts. Yeah, it's also treating 2's complements. Subtracts the value in source RS2 from the value in 1 and puts the result. So yeah, I don't see a reason why you can't use the subtract either, because you know it also treats as 2's complement. So you could, well, although because yeah, actually, you know why this command would be better is because the subtract command is using all registers, you would need another instruction to put a number into a register, then use the subtract. So I guess that's the advantage of using the add I. It's, you can do it in one instruction instead of 2. But that was a good question. I mean, but you know, again, if somebody in this class, you know, if somebody did use the subtract, even though it was required another instruction, it would still be acceptable. Okay, any other questions up to this point? Okay, here's another example. Oh, and you know, if you had done loops like in another programming class, you might have heard, you know, the for loop. So this is basically a for loop in assembly. Okay, here's another example, another type of looping where you can see we come right into a decision point. And again, when you have X5, you know, the X5 here is referring to the contents. This is referring to the contents of register 5. Right, X6, it's the contents of register 6. Okay, so it's making this comparison. And if true, it's going to do some repeated instructions, right? If not true, it's just going to fall out of the loop. So what that would look like in assembly is, you know, we would use the branch of greater than or equal, right? It's going to look at the contents of X5 compared to the contents of X6 and see if X5 is greater than or equal to the contents of 6. If not, it drops out of the loop. If it is, that must mean, or if it isn't, that must mean X5 is less than X6. So that's when we do the repeated instructions, right? We would just keep on doing this until this condition is met and we fall out of the loop. Okay, this is called a while loop. Have you heard these terms before, like for loop and some people nodding their heads? So any questions on this one? Okay, very similar to what we did last week, right? It's just the difference is we have repeated, a set of repeated instructions, right? But we're still using branch instructions like we did last week. Okay, and then this one's a little bit different just because the repeated instructions come before the decision point. Okay, this is a do while. All right, so you would have some repeated code here. And then you're going to do the comparison. Okay, here we're looking at whether the contents of register 5 is less than the contents of register 6. Okay, if it is, we're going to go back to repeated instructions. If not, we drop out of the loop. I told you today's lecture was going to be pretty fast, right? Okay, so any questions about any of these? I would think if you've done looping in a different language, it's very similar to what you've done, right? At least conceptually. The assembly language is different, but the concept is the same. See, that's why flow charting is really nice to know, right? Because this flow chart is going to look the same no matter what language you're writing. The only thing that's going to be different is, the instructions, the syntax, right? That's why I'm surprised they don't teach flow charts in our first program. What do they teach you? Like before you write any code, like in your what? Now they're teaching what Python and so when you took Python, like you just start writing code or oh, I see. So they replace like flow charts with pseudocode. Okay. So you've had some experience with flow charts. I guess I'm just old school, it's just the way I learned, so it's just what's hardwired in my brain. Okay, but let's go ahead and just like I've done in the previous, let's turn the camera. Okay, so just like in the previous software classes, I go over one of the parts of the assignment and then you do the other one. Okay, so I'm going to go over part 2 of software number 3, and then your assignment is doing the first part of it. Okay, so this second part of software number 3, it just tells us that we got this 32-bit value, or we're getting a 32-bit value from the switches. I forgot to put the 0x here. Make sure it's right, but you've done that before, right? The switches exist at address 11.0.0.0. So we're going to input this 32-bit value from the switches. We're going to delay a half a second, and then just output that switch data to the 7th segment, which again is at this address, okay, which is 40 hex from where the switches are at. Okay, now in order to understand, what we're going to do here, there's some information that I think I've mentioned some of this, but not really paying a lot of attention to it yet. But the first thing that we need here in order to do this problem is we need the period of the basis 3 board. In the basis 3 board, you might have learned this in 133, and I think I mentioned at the beginning of this class. It runs at a frequency of 100 megahertz. Okay, that's what, on the basis 3 board, if you look at it, like on the back of it, there's a little like crystal device, and that crystal has a frequency of 100 megahertz. So if you have a frequency of 100 megahertz, what's the period, or how would you figure it out? Yeah, it's just 1 over the frequency, right? Period and frequency are reciprocals, right? So what is that? Does anybody have a calculator, or does anyone remember from 133? Say it again.
10 minutes.
You are right. It's 10 nanoseconds. What's nano? 10 to the what? Very good. -9. 10 to the -9. Now the otter, as you're going to see, and again, I might have mentioned this, but you're going to see how this happens later in the quarter, because see, once you have your otter all built, right? You've done all the pieces, And then you connected all the pieces together, right? And hopefully it's a working, functioning otter. There's circuitry that goes around the otter. Okay, it's called a wrapper. Okay, it's a circuit that Dr. Hummel designed. And what that wrapper, okay, which is a circuitry that goes around the otter does, is that it interfaces the otter to switches and LEDs and 7 segments and keyboards and monitors and whatever other peripherals that you have. Okay, and you'll see it's that otter circuitry that gives the addresses to the inputs and outputs. Like the reason why the switches are at this address is because of what's in that wrapper. Okay, that's where the addresses of the peripherals are determined. Okay. Well, anyway, part of that wrapper is a clock divide circuit that's going to divide the 100 megahertz by a factor of 2. So you see, the otter is going to run at 50 megahertz. So what's the period of 50 megahertz? Right, 20 nanoseconds, right? Because it go down by a factor of 2 in frequency, you go up by a factor of 2 in period, right? Because they're reciprocals. So 20 nanoseconds is what the otter is running at. Okay, that's its, well, the clock frequency is 50 megahertz and the period is 20 nanoseconds. Now, we haven't talked about this yet. Let's see, when will we talk about this? We probably won't talk about this for a few more weeks. But eventually we'll see that most otter instructions, okay, most of the instructions that we have in our ISA, right, our instruction set architecture for the otter, require 2 clock cycles. See, I say most because there are some otter instructions that require 3 clock cycles, okay, but most of them require 2 clock cycles. So if it takes 2 clock cycles and the otter is running at 50 megahertz, which has a period of 20 nanoseconds, how long does it take for an instruction to be processed? 40. Right, 40. See, each clock cycle is 20 nanoseconds, and if it takes 2 clock cycles to do an instruction, well, each instruction requires 40 nanoseconds. So effectively, the instructions are running at 25 megahertz. Okay, that's like the effective instruction frequency, if you will. Okay. So if we want to delay half a second, we can figure out, well, how many instructions that takes, right? How many instructions needed to use up half a second of processing? How would we figure that out? Is it 40 divided by a half? Half a second divided. Yeah, it's the other way around, right? It's a half second divided by 40 nanoseconds. Oh, does anyone have a calculator? Because that's going to come out to a big number, right? If we divide by the small number. What is it? It's 12 billion. What'd you get?
It's a half second divided by 40.
Yeah, it's a half second divided by 40 times 10 to the minus 9. Because remember, 10 to the minus 9, that's nano.
It's like 12 million 500,000.
Check that out. I think that's more than what I got. Does anyone else have a calculator? Did you get the same thing? What did I get? I might have done it wrong. I don't think it was 12. Maybe it was. Oh, yeah, it is. Yeah, it's like 12.5 million. You sure you're not off by one? Yeah, for some reason I thought it was. Yeah, that's right. Yeah, I don't know why I thought it was less than that. I thought it was like. This. It was like 1.25. That's right. So yeah, it takes 12.5 million instructions to use up half a second of processing. Okay, does everybody agree with that? We did the math right? This all makes sense? Okay, so you'll see how this comes into play into our assembly language in just a second, but let's do the flow chart now before we write any assembly code. Okay, so you could have a flow chart that looks like this where, well, you always have a start. Okay, then what are we gonna do first here?
Read a value.
Yeah, we're gonna read from the switches, so that's our parallelogram. So read switches. And what I did is the next thing, just like we did here for the for loop, is, set up a counter and also set up a max count. Okay, where the max count is going to be the number of instructions. So in the flow chart, I mean, I didn't get that specific. I just put, set up registers. Right, because we're going to need a register that's keeping track of how many times we're looping. You're going to see there's a loop coming up. And then also we need a register to hold the total number of instructions, right? Because we need this many instructions to get this amount of delay, this half second. Okay, so then the next thing I have in my flow chart is before we go into the loop, I'm going to increment counter by 1. Okay, and then I'm going to compare this count against the max value. So compare. Compare my counter to the max value. And let's see. Well, I didn't make this big enough. But over here, if not equal, we're going to go back up here. Okay, increment the counter again, and then also, there'll be repeated instructions here. So this is, if it's not equal, we do this. If it is equal, fall out of the loop. Oops. And then this will be outputting to the 7th seg. This is output 7th seg. And we just stop or end.
Where does the if not equal go again? Like if it's not equal, then go to true.
Yeah, I should put it over here. Sorry, I meant it to be inside this thing, but yeah, so. If not equal, sorry. If not equal. So if it's not equal, right, we want to increment again, do the repeated instruction, but if it's equal, we're done with the loop. Okay. All right, so this is what the assembly language would look like. So just like we did over here, because this is going to be a for loop, we have to put, we have to initialize a register to 0. and we gotta put a max count into a register. So we're gonna have two load immediate commands. The first one I have here, I'm using register 6. Well, actually, even before that, we also have to do what, since we're reading data from the switches? Like, what have you done in previous programs when you read from the switches? Right, which requires you to do what first? Like, what do we have to put into a register first to get the data from the switches? Yeah, the address. Right, so that's what I have first. I have loading into register 6, the switch address, like we've done before. And then I have load immediate. I mean, it doesn't matter which order you do this in. I just put this first just because it's something we've done before. But then the next thing is I'm using register 8 for the counter. So I initialize that to 0. Okay, so comment register 8 counter. Okay, then I load the data from the switches. So since it's 32 bits, right, we're using load word. And I'm gonna put the switch data into register 5. And you've seen this before, right, where this number acts as an offset to what you put here, then it uses this as an address, right? Takes the data at that address, puts it into that register, right? You've seen that before. So this will load switch data. Okay, then I use another load immediate. And I'm going to use register 7 for the max count value. So that's where I would put this. That's where I put this 12,500. Although we're going to have to come back and modify this. You'll see in a minute. Because it takes this many instructions to get this delay. Well, actually, no, I take that back. I will work for what we get. Okay, so we're loading this immediate, which is the max count into register 7. Okay, then we do the loop. So once I get into the loop, I'm going to increment my counter. This increments counter. Okay, then I use a branch not equal to, I compare the max count to what the counter is at. And if it's not equal, I want to loop, right? I want to go back. And I just keep doing these instructions over and over again until I reach this time delay. And then once I reach the time delay, then I'm out of the loop. And that's when I write the switch data to the 7 seg. What's the 7 6? Yeah.
Since you use 2 instructions in your loop, should you use half of?
Yeah.
In effect 7?
Right, that's what I was saying about going back and modifying it, that, right, every time we go through the loop, it's using 2 instructions. So if we want half a second delay, we would have to divide this by 2, like you said, right? Because if we left this like this, we get basically a 1 second delay. I mean, there's also additional time for these load immediates, right? Like each one of these instructions would take 40 nanoseconds, but 40 nanoseconds compared to half a second, you can disregard. But yeah, you're right. The way I have this right now, it would actually delay about a second. So we'd have to divide this by 2. So that's what this is. It'd be what? the 6.25 million. Yeah. Again, it's not gonna be exactly a half a second because, there's some added time here, but again, comparing, what's this, like 40, 80, 120, 160 nanoseconds to half a second, because how many nanoseconds in half a second? A lot, right? Yeah, something million, but the point is that we wouldn't worry about the time here. Now, the reason why, this is important is because when you get to, the end of the quarter and hopefully your otter is working and you got it hooked up to the otter wrapper and you download it to the basis board, and there's a test that will have you run on the basis board to make sure that it's working on the board. Well, hopefully you'll get to a point where all that's good, and then you're going to program. And it's likely that in the program that you use for the otter at the end, that you'll need some peripheral like switches or buttons or something. And, it's likely that you'll need to input some data from the switches consecutively. Like you put some data in, and at a time later you change the switches right with different data. Well, in a case like that, you have to delay in your program. You have to have a delay in between when you're inputting different switch data, right? Because if you don't have a delay like this, the program is going to be looking at the switch data in nanoseconds, right? You can't change it that fast. So you got to put a delay that gives you enough time to change the switches. So the data that you want, the subsequent data that you want is there at the time the program is loading it. Okay, so having a program like this is something that more than likely you're gonna need. Now, there's also programming you can do where you're not using the peripherals. Like we'll talk about, we have already talked about just very superficially that in the memory module, there's that segment, that data segment. Well, you'll learn in about, let's see, I think the same day as the midterm, which is a good segue into the midterm in just a minute. Because the midterm's only an hour and there's a lecture after the midterm. Well, the day of the midterm, after the midterm, we talk about how you can set up an array of data in that data section of memory. So you could have a program that just gets the data from memory. It's not getting it from like a peripheral like switches. So it just depends on, what you do for a program. But a lot of times people are using switches, and in a case like that, you'll have to have something that causes a delay. Again, give the user time to change the position of the switches. All right, so do you have any questions about what we did here?
How would you test that?
Yeah, you can't test it in the simulator, right? It's funny you asked that because I am doing that right now. Because in preparation for when you guys get to the final project, I'm trying to do a final project and I'm having problems right now with this. And it's weird because it works in RARs, because in RARs, of course, you're not gonna step through, 6.25 million times, right? So you just put in a smaller, just to see that, it works for, at least maybe like a handful of loops, and then, just kind of assume that, hey, if it works for this number, it's probably going to work for the big number. So anyway, what I'm working on right now, it works fine in RARs. My otter works and everything. It passes everything. I even ran, I made a mem file of this and put it on the board, and I even did a simulation in Bravado, and it works fine. But the problem is, and I'm really stumped, is that when I download it to the basis board, it will take the first value I give it from the switches, and it's fine. But then when I go to put in the second value, it's just not doing anything. So I don't know, there's something not quite right, but I don't know what it is yet. So I'm working on it. Hopefully I'll have it solved before you have to do it, or we'll be learning together at that point. But anyway, yeah, it's you just test it on RARs for a smaller number, And then you can also, make a mem file at the smaller number too. Put it into Vivado with, the hardware and everything and test it on the hardware too. Test it in the simulator and then of course test it on the hardware. So in my particular case, it's working on RARs, working in the simulator on Vivado, but it's not still working on the board, even though my board is good because, my auditor is good. So it passes our test. Because you'll see when you get to the point of the very end, to make sure your auditor works, Dr. Hummel created a huge file. It's called an all test mem file, and it tests every instruction. And it takes only 0.3 milliseconds to run through the whole thing. But if you write the file out in hard copy, because I like looking at things at hard copy. I hate looking at a computer screen. It's about this thick, like this thick. So, but anyway, that's fun stuff that's coming up. Now, as far as the assignment, like I said, we did this part. Your assignment is to do part 1 of software number 3. What part 1 is? Let's see, where did I put my? Oh, so it is here. Okay, so if you look at part 1, it says read a 32-bit value from the switches. Assume the 32-bit value is the combination of two 16-bit unsigned values. Split the 32-bit input into two 16-bit values, an upper and a lower. Okay, again, assume both 16-bit values are unsigned, and then you want to multiply the two together, and then output the result to the 7-set. Okay, so it's basically taking the 32-bit data from the switch, looking at it as two separate numbers, two 16-bit numbers, and then multiplying them together and putting the result on the 7-set. Now, as I said previously, normally and for everything except this assignment, you're not graded on how efficient your program is. But what I would like you to do, just to make this a little bit more challenging, and it's not a whole lot more, but it's a little bit more. What I would like you to do is when you do the multiplication, right? You get the two numbers and you do the multiplication, do it in an efficient manner, right? Because what if one of the numbers is, I don't know, like 40,000 and the other number is 2? What would be a more efficient way? Yeah, well, first of all, how are we going to do the multiplication? Since we're doing a looping, just successive addition, right? So we're going to be doing successive addition. So if one number is 40,000 and the other number is 2, how would you make your program more efficient? Right, exactly. Yeah, exactly. Use 2 for the counter, right? That way you're just adding 40,000 twice as opposed to adding 2 40,000 times, right? So when you do this part, make sure that you're using a smaller number for the counter. Does that make sense? Okay, so any questions on anything before I talk about the midterm? And then we can get started on the assignment. Okay, so just a few comments about the midterm. And like I said at the beginning of class, this is just a reminder. I haven't changed anything. The date is the same as what's on Canvas. That it's a week from upcoming Tuesday. So not Tuesday of next week, but the following week, February 14th. And it's just going to be multiple choice, true, false. Okay, no problems. It's 60 questions. You'll have 60 minutes, and it starts right at 10 past 8. So if you come in late, then you're not going to have 60 minutes. Okay, so 60 minutes, assuming you come in at 8:10. That's when it starts. And you have to take it in your enrolled section. So if you miss class that day, I'm sorry, you missed the test. Okay, I think about half the class has been coming in on time every day, basically, but the other half, I've noticed, most people are a little bit late, but there's been a few people that are quite a bit late. So you don't want to be late at all on that day in particular, right? Because if you're late, you lose that time. Now, I didn't put it up there, but the material will go from the first class all the way through next week. Okay, next week, you'll be building 2 more parts of the hardware. Okay, there's no software assignment next week, it's all hardware. If I remember right, Monday is gonna be the ALU and the immediate generator, and then on Friday will be the branch condition generator and branch address generator. Now, it sounds like a lot, but actually the code that you need for those pieces of hardware are less than what you've been doing for the program counter and also the reg file. Okay, like you'll see that ALU is just one big mux. Okay, so you just have one case statement. And then the immediate generator is like 5 assigned statements. And then the branch condition generator is like 1 if statement. And the branch address generator is like 3 assigned statements. All right, so the coding for the hardware next week compared to what you've done the first 2, I would say is easier. Where the modeling of the Verilog is going to get difficult is when we do the control, okay, but that won't be till after the midterm. Okay. So the material, like I said, goes from the beginning all the way through next week. And, you know, what I would say, although again, I can't give any guarantees, of course, but I would think that someone that's been coming to class, that's been doing the work, you know, that's been conscientious in doing the assignments, you know, participating, not letting the other person do it, but, you know, participating. I would think this wouldn't be anything to stress over. Okay, you would probably, no, the thing is, you never want to go into a test unprepared, right? Never go into a test cold. That's never a good idea. But I would think if someone prepares and they've been coming to class and things have been making sense and they've been doing the work, I would think it shouldn't be something you have to stress over. Okay, now remember, I made recordings of the lectures, so you know you could review those. And also, if you haven't already noticed, on Canvas where I post the videos, I have basically an outline of my notes, actually more detailed than my notes. So you know, you probably want to go through that and review. Okay. Okay, and then the last thing is guessing is discouraged. Okay, so if you look at what I have up here, you know, a correct answer is a +1. If you leave an answer blank, it's a -1, but an incorrect answer is -1.5. Okay, so you don't want to be guessing. If there's a question you have no idea, you probably should just leave it blank, unless you're very good at like the lottery and you know how some people always win like raffles and stuff like that. If you're one of those people, you know, maybe guess. But if you're like me, where you know I've never won anything in my life, you know, I would leave it blank. And then, you know, if you have a question you're not sure about, then it depends on your risk tolerance, right? Whether you're a CD person or whether you're a mutual fund person. Right? Okay, so do you have any questions before you get started? Because you get the rest of the time to work on your assignments. You know, the reg file should be the priority if you didn't finish that, because that's due tomorrow. And then, you know, this software is due on Monday. Software number 3.
Yeah, so, it's an output.
Oh,
Goes into, so I was kind of confused.
Yeah, I'm sorry. Yeah, one, that's not part of the reg file.
Yeah.
The reg file.
Yeah, this is the input. If you look on the diagram and inputs from the PC counter is 32 there. Yeah.
I think it's under otter. Otter. Or yeah. Right, but you see, when you're modeling your job, you're just. Yeah.
So I've got, well, but so then we'll have to.
Well, in the section that you were asking about, it's the top section where you declare your inputs, you just have to declare enable, I just want to understand the relay, those are your inputs.
Okay.
And then these two out.
And then what handles the 32 bits? How's it gonna handle this?
Well, that you have to do in the code, you can.
Well, I mean, eventually, right now, obviously, input those bits myself in the set.
Right, yeah, when you connect this all together,
Eventually.
you make like a signal, and then that signal, you can just put the signal, then in brackets, put those
okay.
bits, just like, and it will just like parse out the bits.
Okay, cool. And then, for my last question, I want to know if it really is the simple. It's async, but you said, if this was correct, I mean, it's correct. You have your RAM. Well, then you just have two assigned statements. It's continuous. With a,
Well, for output.
because
Yeah, actually, that came back. No, it's like, the first thing is that, when we're using the economy, it's always happening. I mean, regardless of what.
So then that's it.
Well, it's, I'm trying to remember what I had on the board, but yeah, after you declare your ins and outs. And then you create the array,
Yeah,
right? You did that,
and then you just make sure you have the right.
right? That's the big thing. Yeah, and then, yeah, what I did is initialize the rate to 0.
Oh, okay, so I was trying to do always come off for async, I was like. I couldn't
No.
make sense, but
Well, there's a way to do async within and always FF. I would just use the assign statements. Yeah, so it's declare the in and outs, create the array, initialize the array to 0, then the assign statement. And then you're gonna need an always FF for the sync plates.
Yeah.
And that's where you can put, make sure it's never not. I didn't say.
Yes. And yes. So you have your. So one cycle you have to. On one cycle, you have to write the data. Right? So you have to write the data. Yeah, you're saying they have like just the KW, but enable us to copy. You tell it. Right, so, but in order to really that, make sure that the data and reading, you have to have something on the register. I want to make sure that it's doing something. Device into the even though you're in another circle. Yeah.